Hello everyone, I am Deepika Gupta, TA for this course on optical methods for solids and fluids. So, we have already seen how to implement a DIC algorithm and how can we capture the images while experimentation. So, there are briefly three important parts in this in situ analysis. First is how do you capture the images when you do the experiments. The second part is to analyze that images, and third which comes is the post processing. So, I have already shown you how to capture these images and how a typical experimental DIC setup looks like. So, today I am going to show you how can you analyze that images on your own. So, we have briefly looked upon how can you write a code from scratch and implement by yourself, but fortunately we do not have to write codes all from start. There are some open source DIC softwares which are available. So, we can just directly input our images and interpret the results and save the results for our further post processing. So, today this session we are calling as a DIY do it yourself DIC session. So, by the end of this session you should be able to implement this analysis on your own and save the results. So, a brief outline for this session is, first I will show you what this open source software which is called as NCorr is, and I will also show you how you can install this software on your system. Then I briefly mention and explain what all terminologies we are using, and then we will analyze some example data sets to get familiar with this software. So, as we have already seen in our previous lectures that how a typical iterative algorithm for DIC can be developed by just using a minimization of a correlation coefficient. So, we have used the definition for the correlation coefficient which is f minus g whole square by f square, where f was our reference image and g was our deformed image in our case, but this is not necessary that we use the same correlation coefficient definition. So, in this open source software we will see that the correlation coefficient definition they will use is slightly different, but the basic formulation for this algorithms same, and it is just developing this iterative technique for getting deformation field that is this p iteratively while searching for minima for the correlation coefficients. Okay. So, if let us say we want to implement the codes by our own, we have already seen that we need to first create a grid, and after that we need to search for this like red region and yellow region I am showing on the screen. So, this basically red region is in the reference configuration and yellow is in the deformed configuration. From the red region we will take a small part which we call as a subset and then search for this small region in the deformed configuration, which we call as a this larger region is which we call as a search window. So, the same idea will be used in the open source implementation also. So, this will help us understand the meaning of various parameters that we will see in this implementation. And once we have this search grid setup, then we search for this correlation peaks or valleys based on what definition we are using iteratively, and then get this final deformation fields. And in this process there were some issues that we briefly mentioned last time in the lecture. So, this is how a typical displacement fields look like, but if you see in this search process we end up with the issues such as this discontinuities across the subset search the regions. So, that we have to handle using some type of curve fitting or some type of interpolation techniques. So, we will briefly see how these issues also are addressed in this open source algorithms. Okay. So, before we start I will just briefly mention what all prerequisites are required for this implementation. First, you need to have a MATLAB version later than 2009. And we will need internet connection because we have to install this software from their website. And in the MATLAB we need two toolboxes. First is a image processing toolbox and the second one is the statistics toolbox, and in MATLAB we need to have a C++ compiler coupled. So, I will briefly show you how to do all this process by yourself. So, okay, let us get started. Here is the website which is this NCorr.com. So, this software was developed by Justin Blaber and his team and maintained from Georgia Tech and maintained by him. He also has a GitHub page. So, you guys can see the updates of this software on his GitHub page, but today I am just going briefly over this implementation. So, on this home page you can see the introduction of what all this software is capable of and how a typical DIC algorithm works, which we have already seen in previous lectures. So, we will just directly go to the installation part. So, once we go to this downloads, we see that on the left side of the screen this three sections are there. So, this is the main source code that you have to download. So, once you have this, you are going to have a zipped file which you can extract in one of the folder. Here we have also the manual where all the information that I will be giving also and how to install and everything you can find here. In case you have any problem installation, you can refer to this manual also. And there are these sample images which you can just use and implement it by yourself. So, I will use one of this test case also today to show you how to implement this analysis and we will go over them one by one. Okay, so, I have already downloaded these files. So, these are the files that you will get once you have extracted the zipped files from the folder. After that we just need a MATLAB. So, we will open a MATLAB on our system. So, here in the MATLAB first we need a C++ compiler and two toolboxes. So, to get these toolboxes you can just go to home on the MATLAB GUI and then open this add-ons. Here in the search panel you can type image processing toolbox. So, this is the toolbox we need. So, I have already added this toolbox in my MATLAB, but in case if you do not have it, you can just add it from this search panel. Here I have already added this toolbox in my MATLAB. So, it is already showing to manage, but if you do not have this toolbox, it will show an option to add. So, you can just add it. The second toolbox that we need is a statistics toolbox. Yeah. So, this is the toolbox that will require for this open source algorithm. This also I have added already. The third we need to add is a C++ compiler. So, this is the C++ compiler that that in general works for Windows. So, you can just add this compiler. So, once you have done this 3 steps, you can just close this window and first let us add this C++ compiler. So, we just have to type max setup C++. So, in case if you do not have a C++ compiler, it is going to set up this compiler. So, in my case it is already configured. Then start our installation. So, we have to type this handles NCorr equals to NCorr. This will automatically install all the files of this software, and it is asking me to add the path. In your case it might like when you are doing the installation for the first time, it might ask you for few more information. So, you can just click yes, and it is going to ask you to add the cores which are there on your laptop. You can check how many cores your system has in by just going to a task manager. So, here in the performance option on the you can see how many cores. So, my laptop has a 4 cores. So, I can give you give 3 or let us say 2 cores to this open source software while installation. So, on the basis of how many cores you have, you can assign all 4 also, but other processes in the system will get slow if you add all 4s for this software. Now, we can just add path. Once you have added path, it is going to open a GUI like this, or the one shown on the screen. So, let us go over different terminologies or different functions which are there here. Okay. So, as we know already that what is the first step to implement any DIC algorithm? First step is to load the images. So, the same in the same way we have option here to load the images. So, first option is load a reference image. So, these are the 3 sample examples which are there in NCorr website. So, I am going to use this first sample plate hole example. So, 0 0, this is the first image which I am loading as a reference image. Okay. So, once this image is successfully loaded, you are going to see a image which you have loaded in this reference image panel. The next step is to load current images. So, now on the screen we can see that there are 2 options to load a reference image. One says load all and the other one is load lazy. So, load all is a option which is going to load how many, let us say you have 100 images, it is going to load all 100 images at once, and load lazy is when you are loading all these images one by one. So, we will just do load all and go to the same folder and accept the first reference image. I am going to load all rest of the images in this current images configuration. So, I can see all the 11 images in this current image section. So, here all 11 images are loaded successfully. So, once we have done that, what is the next step? So, in our code implementation also, the next step is to define the region of interest, which is the region where we want our deformation field. So, this is what we do while we do masking. So, there are 2 options here. One is set reference region of interest and other is set current region of interest. So, in case of forward analysis, which we have seen in our lectures, we need to set the reference region of interest. Backward analysis is something little bit different. The details of that I am just going to skip for now, but it is also the same. It is just that in spite of taking a small subset from reference image and searching in the deformed image, you will take a subset from a deformed image and in some sense undeform it and select for and search for that region in the reference image. So, what we have seen in our lecture is what we call as a forward analysis. So, okay, we will just click this set reference region of interest configuration. Now, here we can see there are 2 options. One is load region of interest and other is draw region of interest. So, if you have the mask made already and saved in the same folder, you can just do this load region of interest option and go to that path where you have the region of interest. Here in that sample images, they have already given the mask. So, I can just take it and load the region of interest and click finish. The other option is to draw it. On this screen itself, we can see there are multiple options to draw the region of interest. So, I can just select whatever the option is suitable. So, for example, I have just drawn the rectangle. Now, I want to subtract this small circle. So, we can just choose the minus ellipse option and then draw it, and that is how we can select or set the mask. So, I will just use the same mask that they have given. So, I will go to the same path, set this region of interest, click finish. So, now we have already selected what is the region where we want our deformation field. So, once we have loaded the images, defined the region of interest, like next step is to set the parameters for the DIC. analysis. So, as we have already seen, the first step is to make the grid. So, now you can relate all this relate all this parameter to the method that we have already seen. First, you are seeing here is the subset radius, which is the size of the subset which you will take from the reference image and search for it when while correlation, right. So, we can set the subset radius based on what is the size of our speckle patterns. Let us say we have 2 fine speckle patterns, then we can set subset radius which is less and get more resolution, but we need to be little bit careful while we set the subset radius. So, for now I am just setting the subset radius to 30. Now next step is the subset. What is the size of the grid? This subset spacing is going to decide that. So, I can just set the subset spacing for now to be 15. Now, next option you are seeing is a difference of norm. This is the parameter which is going to affect your iterative scheme. So, if you remember from the lecture, so when we search for p, we say that okay, when our p r plus 1, that means deformation in next iteration and deformation in the current iteration, when their difference is less than some limit, will stop our iterative solver. So, here this is the parameter which is going to decide that what is the difference when we stop searching. So, here we are just setting this limit to be 10 to the power minus 6, which is good enough. So, iterations is the maximum number of iteration. Let us say when you are searching in iterations, we are not finding any convergence. So, what is the maximum number of iterations till it is going to search? So, usually in correlation searches, if your speckle patterns are good enough and you have selected a correct subset size, the solution converges within 15 to 20 iterations easily. So, 50 is a good enough number to set. Now, next option is multi-threading options. So, in this software, they allow us to search for correlation parallelly in multiple regions, which saves us some time. So, this depends on how many cores we have assigned already. So, right now we have I have assigned 4 cores. So, I can just give number of threads as 4, which will parallelly search for 4 different regions and give me the final deformation field. Okay. Now, here is something interesting in the next option, which is high strain analysis. So, let us say our experiment includes very high strains and we have taken images. So, when we search, we have to have one reference image and one deformed image, right. But there are 2 possibilities now. Let us say I have 1 to 10 images. Now, one is my reference image and in every iteration I am taking the same reference image. So, I will just correlate second with first, third with first, fourth with first. But if strains are very large or let us say deformations are very large, at some point my correlation between the first and let us say sixth image is not good. So, I need to update my reference image when I move forward. So, this is the option that enables us to update our reference image. So, there are 2 options here. One is seed propagation. So, let us say my first and sixth image at my correlations are not good. So, there is already one criteria. So, which will check whether the correlation is good or not. If correlation is bad, it is going to auto update the reference image. But let us say we do not want to do this and we want to manually select that after every 5th image reference image should be updated. So, we can select just this leapfrog option and give what will be the step when we want to update our images, update our reference image. So, let us say I am just assigning 2, which means every third image will have a new reference image. So, this is all when we set this DIC parameters. Now, another option is for the discontinuous analysis. So, when we have these options where we have a hole or a crack where we do not have a proper speckle patterns, we need to truncate our subsets at the boundary, so that in that regions our correlation coefficient search is not getting affected. So, we need to select that this option subset truncation in that case. So, I am just not selecting as of now, but you can try and implement it by your own. So, I will just click finish. So, it is saying so here I am getting a message that there are points in the ROI near the edges of the image. This point can cause problems when the ROI is updated. So, if you remember, we are searching for subset from the reference and finding the correlation in the deformed image, right. But let us say my subset which is there in the reference image, now the deformation is so much that it has gone out from the region of interest. In that case, I am going to have the issues, because there is no deformed configuration for that particular subset. So, in that, to avoid this, we will leave out the boundaries of the images where the possibility of subsets going out is more. So, right now we have selected the mask that they have already given in the images, that which goes to the full length of the image, I mean the size of the image, that is why we are getting this error. But let us say if we select a region of interest within the image, this error will not show. So, I will just click OK, because I am just showing you how to analyze. So, which is OK. So, we will just click yes. So, now we have set already our DIC parameters which are there. So, now the next step is to perform the analysis, because we have already set all the parameters, loaded all the images. So, we will perform this DIC analysis. Now, here it is asking us to select the region. So, this is the region where we want to do the analysis. So, if you see the option, it is asking me to set seeds. Now, what are these seeds? So, we have already seen that we need to have an initial guess when we start the DIC iterations, right. So, in this case, this initial guess will be calculated only at few points. So, let us say I have a grid, and on that grid I am starting to search on all the grid points for the initial guess. It is going to take lot of time. So, instead of that we will do search only for one point, and then use that result as an initial guess for the neighbor points. So, we will just set seeds. This is the one functionality of this setting seeds. The other thing is it also helps in this multi-threading options. So, it is going to, so these 4 regions are going to go into separate threads and analyzed parallelly while search. So, I will just click finish. Now, it is processing the seeds. Now, here is one check that you can do whether you have set your subset size, grid size correctly or not. So, it is showing me that iterations have converged within the 4 steps, and the norm of difference vector is 10 power minus 7, which is good enough, and the correlation coefficient was 0.0039. So, that means the seed points have good speckle patterns. In case if your speckle patterns are not good, either you will have very large number of iterations, for example, maximum iterations will be encountered and still you will not have a good convergence or this norm of difference vectors. So, this way you can check whatever you have parameters set in the DIC analysis, are they good enough or you need to change something. So, that is how you can judge also. Okay, so, we have selected 4 seed points already. Now, it is showing us processing images. So, this is going to process all the images with the reference images that we have set, and now our analysis is complete. So, we now have the results for displacements and strains. Next step is to format the displacements. So, when we take images, right. So, in that case each pixel corresponds to some physical unit. So, let us say my one pixel is approximately 0.5 mm or whatever depending upon your experiments. So, you can set that scale and convert this results into the actual physical scales that you understand. So, as of now we do not know what is the scale of the images. So, we will just leave these options. Now, the next option is to set the correlation cutoff. So, right now it is showing us this correlation cutoff of 0.0083. Just to show you, let us say if I set the cutoff to 0, so we can't set the cutoff to 0, it is saying that. So, let us say just to show, let us say I have set the correlation cutoff. Okay. So, okay. So, this correlation cutoff, actually what it does, in some regions if let us say your correlation is not good and you are setting a correlation cutoff. So, it is going to drop the results from that region. So, as you can see on the screen that it has dropped the regions on the right hand side of the image, because there was the correlation cutoff which was approximately 0.08, which is good enough, but just to show you what it does, I have used I have shown the functionality of this option. The next thing, it asks us lens distortion option. We do not have to change anything here, because this is what depends on the camera and experimental observation. So, we right now we do not need to bother about this lens distortion option, and we will just click finish here. So, it is showing us all the correlation coefficient cutoff for images till 11, and it is asking is this correct. So, we will just click yes. So, now our all displacement fields have been formatted according to whatever options we have selected. Now, next option is to calculate the strains. Okay, so, if you remember, we have already mentioned that when we search for correlation using the subsets on the grid, we get the issues of discontinuities across subset boundaries in this local DIC scheme. So, this taking the subset from one small grid center and then searching, this is what we call as a local DIC scheme. So, at the end we need to have some type of interpolation or some type of curve fitting, which will help us avoid that discontinuities issue. So, what it does, it takes a small radius and fits the surface to all the data which is there within this small radius. So, let us say my radius is 10, you can see on the right hand side of this screen itself that it is fitting a surface to all the data. So, which is there in this displacement. So, strain radius we can search according to the data that we have in the experiment. So, as of now I am just assigning this as a 10. Now, the other option is Lagrangian and Eulerian strains. So, there are we know already that there are two types of strains that we can define, either with respect to deformed configuration or with respect to the reference configuration. This is what that option is. Now, we can look for u and v displacements if whatever strain radius we have assigned, whether it is correct or we need to change it. So, okay. So, strain radius 10 is showing us good enough for smooth deformation field without any spuriousness. So, we will just use that and click finish. Okay. So, now we have already analyzed all the displacement fields, strain fields for the whole set of images. So, now the next step is to plot. Let us say I want to see what is this x displacement field looks like. So, I can see, and for all the images how the displacement fields look like, and we can see that this plate with the hole was getting stretched when we were when the images were taken. So, that you can see here. Let us look at how V displacement fields look like. So, see the direction of stretch was in V direction, that can be easily interpreted from this displacement results. So, that is how we can do an analysis. Now, you can just capture the images of your experiments use some air spray or some other way of giving the speckle patterns, and just use this open source software to analyze them. Now, I will just briefly show you how to save all this data, because let us say at the end we want to save the data and use it for further post processing, right. So, on in this file option they are giving us the option to save the data, and the data will be saved in .met format, which you can read further for further post processing in the MATLAB. So, I am just assigning as a sample plate whole. So, now this data is saved. Here if you see, this is the file that we have just created. So, okay, I am just double clicking. So, or else you can just write in the command window load and this file name in the quotes. So, it is going to load all the data which was there. Now, here you are seeing this current save option, so which is showing all the files, and here is all the DIC data. So, these are the data for the displacement fields. We have u, v, and whatever correlation coefficients were there. Then there are this displacement information that we had assigned while performing the analysis. Then we can also see whatever strains we have assigned. So, we can see that the grid size was 65 by 25. So, there were actually 65 by 25 grid points where we had performed this analysis here. So, at each grid point it is giving us the value of the deformation field. So, hope this session helped in getting the brief introduction of how you can implement your DIC algorithm in this open source software and analyze your images. And you can just try all other data sets which they have provided, or take your own experimental data sets and use this software in spite saving some effort in writing your own codes and get the good deformation fields. In any doubts, you can always go back to the manual which is provided on their websites, and you can write to us also. Thank you.